In the vast, infinite darkness of space, some 13 billion light-years away from Earth, astronomers have stumbled upon something that defies all conventional understanding. Something so astonishing, so incomprehensible, that it has ignited a scientific revolution and sparked debates across the astrophysics community. Galaxies. Gigantic, luminous cities of stars that, according to everything we thought we knew, simply should not exist. These aren't faint smudges in the distance. These galaxies shine brightly like ancient beacons. They're packed with as many stars as our own Milky Way, possibly more. But here's the enigma. They appear to have formed when the universe was less than 500 million years old. In cosmic terms, that's infancy. It's like discovering fully grown trees in a forest that was planted last week. This revelation wasn't just unexpected. It was impossible, at least according to the current models of the universe. The James Webb Space Telescope, our most powerful eye in the cosmos, captured the first images in July 2022. Scientists around the globe were excited, expecting to see the baby pictures of the universe, dim and patchy glows of primordial gas slowly assembling into stars and galaxies. But what they found instead were massive structured galaxies that seemed to belong in a universe twice as old. Dr. Erica Nelson, an astrophysicist at the University of Colorado, described the moment she saw the data as a crisis in cosmology. These galaxies aren't just big, they're too big, too early, too perfect. It's like walking into a kindergarten and finding fully grown adults in suits having a board meeting. How could structures so vast form so fast with such apparent maturity? To understand the magnitude of this discovery, we need to revisit the timeline of the universe. According to the Big Bang theory, after the universe burst into existence about 13.8 billion years ago, it was a hot, dense soup of particles. Over hundreds of millions of years, gravity gradually pulled matter together to form the first stars and galaxies. It wasn't supposed to be a quick process. In fact, early galaxies were expected to be clumpy, chaotic, and dim. But the ones JWST has revealed are anything but. They're orderly, they're massive, they're old. Some of these galaxies have been named. Glass Z13, for instance, is believed to have existed just 300 million years after the Big Bang. That's closer to the beginning of time than to the formation of our own solar system. And yet, it contains enough mass to rival modern galaxies. The implications? Profound. If these galaxies are truly as massive and mature as they appear, our models of cosmic evolution may need a complete overhaul. It could mean that star formation in the early universe happened much faster than we believed, or that we're missing something fundamental about the nature of space-time itself. And this leads to bigger questions. Are our estimates of the age of the universe wrong? Is dark matter behaving differently in the early universe? Or is there a new force, a hidden mechanism that jump-starts galaxy formation at lightning speed? Astronomers and cosmologists are now scrambling to revise theories. Some are proposing modified models of inflation, suggesting that certain regions of space may have evolved faster than others. Others speculate that we might be seeing the effects of ancient black holes that acted as seeds for early galaxies. But no matter the explanation, one thing is clear: the universe is far stranger, more dynamic, and more complex than we ever imagined. This is just the beginning. As the James Webb Telescope continues to peer deeper into the cosmos, more impossible discoveries may emerge. Every image it sends back challenges our assumptions and invites us to rewrite the story of how everything came to be. So, what if our understanding of time, gravity, or even the Big Bang itself is flawed? What if these ancient galaxies are not anomalies, but the norm? And we, modern humans, are merely latecomers in a much older, grander cosmic story. Stay with us as we dive deeper into this cosmic mystery in the next segment, where we'll explore the specific galaxies in question, how scientists are analyzing their properties, and what it all might mean for the future of cosmology. And remember, in the universe, nothing is truly impossible. In the aftermath of James Webb's first revelations, the scientific world was stunned. What had been expected to be a slow unveiling of the universe's childhood instead turned into a jarring discovery of cosmic maturity far too early in time. The galaxies weren't just there, they were thriving. And their structures weren't chaotic as predicted. They were smooth, coherent, and expansive. This wasn't just about seeing ancient light, it was about seeing ancient complexity. And that complexity challenged our deepest held beliefs. The early universe, as we understood it, should have been dark, scattered, and wild, a realm where matter was still coalescing, where gravity was only beginning its quiet work of pulling particles into stars. But now, thanks to Webb's ultra-sensitive infrared eyes, we were seeing mature galactic ecosystems with defined shapes and unimaginable mass. Some of these galaxies formed within the first few 100 million years after the Big Bang. At that time, space was still clearing its primordial fog, photons only recently freed from the dense plasma of the early universe. The very notion that such massive structures could exist in that environment sent shockwaves through every model and theory on the books. To put it in perspective, if you imagined the age of the universe as a 24-hour day, these galaxies appeared just minutes after midnight, and yet they already looked like the bustling metropolises of stars we see around us today. Their luminosity was off the charts, their rates of star formation blazingly high, some reaching 100 times that of the Milky Way. So how is this possible? One leading theory posits that star formation in the early universe was turbocharged. Maybe the first gas clouds collapsed faster than expected. Maybe the abundance of dark matter provided gravitational scaffolding that accelerated galactic assembly. Or perhaps black holes formed extraordinarily early and fed their surrounding environments with energy, encouraging rapid stellar birth. But even these explanations feel like band-aids. The growth was just too fast, too big. Theoretical astrophysicist Dr. Adam Riess, Nobel laureate for the discovery of dark energy, suggested that we may need to rethink the rules of cosmic evolution. And he's not alone. Some researchers propose that we may be underestimating the role of exotic physics. Perhaps gravity behaves differently in extreme conditions. Or maybe time itself is not as linear and uniform as we've assumed. Other fringe theories suggest interactions with alternate dimensions, or early universe anomalies that defy current models. And here's the real mind-bender. What if the universe is older than we think? The James Webb discoveries have reignited the debate around the age of the universe. While 13.8 billion years is widely accepted based on the cosmic microwave background and expansion rate, these massive early galaxies could suggest a longer timeline. If the redshift measurements we rely on are slightly off, due to phenomena we don't yet understand, then everything from the birth of the first stars to the timeline of galactic evolution may need revision. And that's not all. These findings have sparked an avalanche of new studies. Researchers are reanalyzing datasets, creating revised models, and launching simulations that factor in these impossible galaxies. Some simulations now suggest that intense bursts of star formation might have been triggered by large-scale cosmic web collisions, where filaments of matter intersected and collapsed into massive nodes far earlier than expected. Others are even looking back at Hubble data with new eyes, wondering if we may have missed similar galaxies hiding in plain sight. This is science in action, not retreating from contradictions, but running straight into them. Because every anomaly is an opportunity. and every shattered assumption opens the door to deeper truths. At infinity beyond, we believe these are the moments that define human curiosity, when the cosmos refuses to fit in our equations and invites us to expand our understanding. As the James Webb Space Telescope continues its mission, more mysteries will unfold. But for now, these ancient luminous giants stand as monuments to the unknown, galaxies that whisper a deeper story about the origins of everything. In the next segment, we'll dive into the tools and techniques astronomers are using to verify these early galaxy observations. How do they measure such incredible distances? What exactly is redshift, and why does it matter so much? And could there be hidden biases distorting what we think we're seeing? Buckle up! The universe is just getting started. The discovery of ancient galaxies that seemingly predate the universe has forced astronomers to revisit the very methods they rely on to measure cosmic time and distance. At the heart of these calculations lies a concept that is as elegant as it is critical: redshift. To understand how we can say a galaxy is 13 billion light-years away, or that it existed just 300 million years after the Big Bang, we must first understand how light behaves as the universe expands. When a galaxy emits light, that light begins a journey across the fabric of space. But unlike a beam traveling through a static vacuum, space itself is stretching, and as it stretches, it also stretches the light traveling through it. This causes the light's wavelength to increase, shifting it toward the red end of the electromagnetic spectrum, a phenomenon known as cosmological redshift. The greater the redshift, the farther the galaxy. The farther the galaxy, the deeper into the past we are looking. It's a beautiful system, but it's not flawless. Redshift is the backbone of our cosmic distance ladder. Using it, astronomers can calculate how much the universe has expanded since the light left a galaxy. The James Webb Space Telescope excels at detecting infrared light, the kind of stretched, red-shifted light emitted by very distant, ancient objects. That's why JWST has been able to peer further into the early universe than any observatory before it. But interpreting redshift isn't as simple as reading a number off a gauge. There are two primary ways redshift is determined: photometric redshift and spectroscopic redshift. Photometric redshift is faster. It estimates redshift by analyzing a galaxy's brightness through various filters. Think of it like trying to determine the age of a wine by looking at its color through tinted glass. It can be surprisingly accurate, but it's also prone to errors, especially with very distant objects. Dust, unusual star populations, and even gravitational lensing can throw off readings. Spectroscopic redshift, on the other hand, is the gold standard. It involves splitting a galaxy's light into its component colors and analyzing specific absorption or emission lines, unique fingerprints of elements like hydrogen or oxygen. By measuring how far these lines have shifted, astronomers can determine redshift with incredible precision. Many of the early impossible galaxies detected by Webb were initially measured using photometric redshift. That led some skeptics to question the findings. Could these objects be closer than we thought? Could dust or interference be tricking our instruments? To answer those concerns, follow-up observations with spectroscopic methods began, and the results were stunning. One by one, the redshifts were confirmed. These galaxies truly were as distant and as ancient as the original measurements claimed. Glass Z13, Sears 1749, and others have now become case studies in the reliability of Webb's vision. But these confirmations also deepened the mystery. Because now there was no escape hatch. We couldn't blame faulty instruments or bad math. The galaxies are real, and their existence is rewriting the physics of early cosmic evolution. This has triggered a renewed emphasis on refining our models of redshift and expansion. Scientists are now incorporating variables like early universe conditions, feedback from primordial black holes, and non-uniform inflation into simulations to see if any could produce galaxies of such mass so soon after the Big Bang. It's also reignited interest in alternative cosmologies. Could our interpretation of redshift itself be incomplete? Some theories, though controversial, suggest that what we perceive as redshift might be influenced by unknown quantum effects or interactions with dark energy fields that vary across space-time. Others suggest that light might be aging or losing energy in ways we don't yet understand. A modern revisit of the once-dismissed tired light hypothesis. While most mainstream cosmologists remain skeptical, these fringe ideas are receiving more attention as data from JWST continues to challenge conventional wisdom. What's certain is this: redshift is not just a technical detail. It's the cornerstone of how we measure, date, and understand the universe. And now, it's at the center of a cosmic puzzle that may reshape everything we thought we knew. At Infinity Beyond, we're here to follow that light, however faint, however redshifted, to its final answer. In our next segment, we'll explore what these revelations mean for our understanding of dark matter and dark energy. Could the early emergence of massive galaxies point to a hidden form of matter? Or are we on the cusp of discovering an entirely new force that governs the infant universe? The cosmos is whispering its secrets, and we're finally learning how to listen. As the James Webb Space Telescope continues to peer into the primordial past, its revelations grow more baffling and more profound. With each newly imaged galaxy formed just a few 100 million years after the Big Bang, scientists are faced with an unsettling realization. Something unseen must be at play in the early universe, and that something might be dark matter. For decades, dark matter has loomed as one of the universe's greatest mysteries. It doesn't emit, absorb, or reflect light. It can't be touched or directly seen. Yet its gravitational influence is undeniable. Galaxies spin faster than their visible mass should allow. Cosmic structures form in patterns that betray the presence of a hidden scaffolding. Dark matter is the invisible glue holding the cosmos together, and it may also be the secret accelerator of galactic birth in the early universe. Here's the idea. While ordinary matter, what we're made of, was still struggling to cool and coalesce, dark matter may have already been clumping into dense halos. These halos, though invisible, exerted immense gravitational pull, acting as cosmic wells into which ordinary matter could fall. Once trapped, that matter began forming stars and galaxies, faster and more efficiently than previously imagined. This theory isn't entirely new, but the galaxies detected by JWST give it fresh urgency. Some scientists now propose that ultra-dense dark matter halos formed shockingly early, creating gravitational environments ripe for accelerated star formation. These halos might not just support galaxy formation, they could trigger it at warp speed. But there's a twist. If these dark matter halos were too dense or too numerous too early, they'd have left imprints in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Yet current observations don't show such distortions. That forces theorists to walk a tightrope. How can dark matter be active enough to build galaxies early, but subtle enough not to betray itself in the background glow? Enter new models. Some physicists are now exploring the idea of warm dark matter, particles lighter and faster moving than the traditionally hypothesized cold dark matter. These warm particles might have created smoother, faster-forming structures, avoiding the telltale clumpiness that would disturb the cosmic background. Others suggest self-interacting dark matter, in which particles of dark matter collide and scatter, changing how they distribute gravitationally. In simulations, these properties can reproduce galactic formations that resemble JWST's early discoveries without breaking the observable universe's rules. Still, these ideas remain theoretical. No one has directly detected a single dark matter particle. The Large Hadron Collider has come up empty. Deep underground experiments have yielded only silence. But the cosmos is speaking, loudly, and it's telling us that whatever dark matter is, it plays a critical role in shaping the universe. And what about dark energy, the mysterious force accelerating the expansion of the cosmos? While dark energy dominates the universe today, it's thought to have been less influential in the early universe. But what if that's wrong? Some fringe hypotheses suggest that dark energy may have had surges of activity, brief eras of repulsive force that shaped large-scale structure far earlier than we expected. These surges could have accelerated matter away from voids and funneled it into dense regions, catalyzing the birth of massive galaxies. Alternatively, dark energy may not be a constant at all. Some models propose it evolves over time, or space, like a dynamic field that pulses with varying strength. If such pulses occurred shortly after the Big Bang, they could explain the unusually rapid growth of cosmic structures we now observe. The truth is, we are just beginning to grasp how the invisible universe shaped the visible one. The galaxies that Webb has revealed aren't just outliers. They're signposts, clues to a deeper architecture of existence. One held together not just by gravity and atoms, but by forces and particles we have yet to comprehend. This is the frontier where physics meets philosophy, where questions outnumber answers, where models strain and mystery thrives. At Infinity Beyond, we believe that these are the most thrilling moments in science, when nature teases us with evidence that reality is stranger, richer, and more wondrous than we dared to believe. In the next segment, we'll dive into alternative cosmological models that challenge the standard Big Bang narrative. Could the universe have started differently than we think? Are there other explanations for the early galaxies besides dark matter? And what if the entire history of the cosmos is due for a rewrite? Stick with us. The journey through the unknown has only just begun. For nearly a century, the Big Bang theory has been the cornerstone of modern cosmology. According to this elegant model, the universe began as a singularity, a point of infinite density, and has been expanding ever since. It explains the cosmic microwave background, the abundance of light elements, and the large-scale structure of the cosmos. But now, with the James Webb Space Telescope uncovering massive, mature galaxies that formed just a few 100 million years after this supposed beginning, scientists are asking a bold question. What if the Big Bang story is incomplete, or even wrong? The early galaxies Webb has revealed don't behave like newly formed structures. They're organized, luminous, and impossibly old-looking. That doesn't fit the chaotic, turbulent beginnings that standard cosmology predicts. So what's going on? Let's start by revisiting what the Big Bang actually is, and what it isn't. Contrary to popular belief, the Big Bang wasn't an explosion in space. It was an expansion of space itself. There was no outside into which it exploded, because space and time themselves were born in that moment. But this raises a fundamental issue. If time itself started at the Big Bang, how can galaxies exist that seem older than time? Some scientists are now exploring alternative cosmologies, radical new models that challenge the standard narrative and attempt to explain the anomalies JWST is revealing. One such idea is the Big Bounce model. Instead of a singular beginning, this theory proposes that the universe is cyclic. It contracts, collapses, and then bounces back into a new expansion. In this scenario, the current universe may have inherited structure or even matter from a previous cosmic cycle. That could explain how some galaxies seem more evolved than they should be. Another proposal is the emergent universe model, which suggests that the universe existed in a static state for an infinite amount of time before undergoing rapid expansion. In this version, Galaxies or galaxy seeds might have begun forming long before what we call the Big Bang, giving them a massive head start. There's also the variable speed of light hypothesis, which posits that in the very early universe, the speed of light was much faster than it is now. This would allow light, and therefore information and energy, to travel farther and faster, enabling structures like galaxies to form more quickly than standard models allow. Then there's the idea of quantum gravity pre-Big Bang models, like loop quantum cosmology. These suggest that what we perceive as the beginning may just be a transition point, a bounce from a previous universe governed by quantum gravitational rules. In such a universe, time doesn't truly begin. It merely turns a corner. But perhaps the most mind-bending notion of all is that our entire cosmological model is based on flawed assumptions about time and causality. What if time itself is not linear? What if the arrow of time is an emergent property, one that behaves differently under extreme conditions? In this view, the early universe may not have been bound by the same cause-effect logic that governs our daily experience. Structures like galaxies could arise spontaneously, not through gradual formation, but through quantum processes that defy classical thinking. And then there are multiverse models, which propose that our universe is just one of many, a bubble in a frothing cosmic sea. If true, the conditions in our universe might not be typical. We may have formed in a rare pocket of space-time where galaxies assembled faster, earlier, and more efficiently than the average universe. Webb could simply be revealing that we live in a special, statistical outlier. Of course, these ideas remain speculative. They push the limits of both observation and mathematics. But that's precisely where breakthroughs often lie, in the space between what we know and what we dare to imagine. The early galaxies discovered by JWST are not just outliers. They are provocations. They challenge the Big Bang not by refuting it, but by demanding its evolution. Science thrives on such tension. It is in the friction between theory and observation that progress is born. At Infinity Beyond, we're not afraid to question the big ideas. We embrace the unknown, not as a void to fear, but as an invitation to explore. In our next segment, we'll explore one of the most controversial ideas in modern astrophysics. Are we misinterpreting the data entirely? Could the galaxies we're seeing be distorted by gravitational lensing, quantum mirages, or even observational bias? Or are they truly what they seem? Echoes from a time that shouldn't exist. Join us as we continue to unravel the greatest mystery of all. Where and how did it all begin? As the mysteries of the early universe pile up, a sobering question emerges. What if we're wrong? Not about the universe itself, but about how we're seeing it. The James Webb Space Telescope has given us stunning, paradigm-shifting images of ancient galaxies that shouldn't exist. Not this soon, not this massive, not this mature. But before rewriting the laws of physics, some astronomers are asking whether there's another explanation hiding in plain sight. Cosmic illusion. Let's start with a phenomenon known as gravitational lensing. Predicted by Einstein's general theory of relativity, gravitational lensing occurs when a massive object, like a galaxy cluster, sits between us and a more distant object. The immense gravity of the intervening mass bends space-time, curving the path of light and magnifying the background object. It's like looking through a cosmic magnifying glass. Gravitational lensing can make distant galaxies appear brighter, larger, or even multiply their image. In extreme cases, it can take a faint, ordinary galaxy and make it look like a massive ancient behemoth. So, are the galaxies seen by JWST really as big and bright as they appear? Or are we looking at lens delusions? Some scientists argue that gravitational lensing could be responsible for at least a few of the impossible galaxies spotted so far. But this explanation has limits. Lensing leaves telltale signs, warped arcs, multiple images, and many of Webb's most stunning early galaxy candidates show no such distortions. Moreover, careful analysis has been done to rule out lensing in several key cases. These galaxies appear to be exactly what they seem: real, ancient, and massive. Still, illusion remains a possibility, but not just due to gravity. There's another factor: observational bias. Webb's field of view is narrow, and its early surveys focused on small patches of sky. What if, by sheer coincidence, we've stumbled upon a few extraordinarily early overachieving galaxies that don't represent the cosmic average? In other words, what if we're overreacting to cosmic outliers? It's a valid concern. Astronomy has a long history of jumping to conclusions based on limited data, only to refine the picture as more observations roll in. But the number of high redshift, mature galaxies JWST has detected is already well beyond what standard models predicted. These aren't isolated cases, they form a pattern. Even so, another potential illusion comes into play: cosmic mirages created by quantum effects. At the most fundamental level, space-time may not be smooth, but foamy, a turbulent sea of quantum fluctuations. Some speculative theories suggest that light traveling billions of years across this foamy structure might accumulate small shifts in energy or trajectory, causing distortions that mimic high redshift. If true, this could inflate the apparent distances and ages of galaxies we observe. Then there's the possibility of unknown intervening matter, clouds of gas or plasma that subtly shift the light's signature as it travels toward us. Could these distortions be making ordinary galaxies appear older or more distant than they truly are? Most mainstream astronomers remain cautious about these fringe ideas. But as JWST continues to send back data that challenges our models, more scientists are taking a second look at assumptions long held as fact. And let's not forget the role of our own instruments. Even a telescope as advanced as Webb must interpret the faintest whispers of ancient starlight. Every image is a data-rich mosaic stitched together from complex calibrations and filtering algorithms. A minor miscalculation in background subtraction or photometric fitting could skew a galaxy's estimated redshift, and therefore its perceived age and size. That's why spectroscopic confirmation is crucial. Already, multiple JWST targets have been verified using spectroscopy, affirming that their redshifts, and therefore their ancient origins, are indeed real. But not all candidates have been confirmed yet. Until they are, the door remains open to alternative interpretations. So are we witnessing a fundamental flaw in cosmology? Or are we simply being deceived by the cosmos, fooled by gravity, geometry, or even quantum trickery? The answer may be both. The universe is under no obligation to be easily understood. It speaks in light stretched across time, through space twisted by mass, through signals filtered by chance and dust and energy. Our job is to listen, not just with our instruments, but with imagination tempered by rigor. At Infinity Beyond, we embrace the possibility that the greatest mysteries aren't always what we see, but how we see. Every revelation from Webb is both a discovery and a challenge, a call to refine our vision. In the next segment, we'll explore how these cosmic revelations are shaking the very foundation of modern physics. From the constants of nature to the shape of the universe itself, nothing is immune to scrutiny. What if even the laws of physics evolved over time? What if reality is more flexible than we ever imagined? The James Webb Space Telescope is not just showing us distant galaxies. It's exposing the cracks in our most cherished understanding of reality. What happens when discoveries from the edge of the cosmos begin to challenge the very laws of physics themselves? Until now, physics has relied on the idea that certain quantities, like the speed of light, the strength of gravity, or the charge of an electron are constants, immutable, unchanging. These constants are the bedrock of the universe, defining how matter behaves, how stars burn, and how galaxies evolve. But what if they haven't always been constant? The early universe, as observed by JWST, is not behaving the way we expect. Galaxies are forming too quickly, masses are building too early, and structure is emerging in apparent violation of our cosmological models. One possibility, among the most radical yet scientifically intriguing, is that the laws of physics themselves may evolve over time. This idea is not entirely new. Physicists have long speculated that certain fundamental constants could drift under extreme conditions or across cosmic timescales. The fine structure constant, for example, which governs how light and matter interact, has been tested in distant quasars. Some results suggest it might vary slightly across space or time. If true, even a tiny variation in this constant in the early universe could result in massive differences in how atoms formed, how stars ignited, and how galaxies took shape. Then there's gravity. We think of gravity as the weakest but most far-reaching force in the universe. It governs the motion of planets and galaxies, but current models assume that its strength has remained the same since the beginning of time. Now, some theorists propose modified gravity theories, like FER gravity or scalar tensor models, where the gravitational constant is not constant at all, but dynamic. In these models, gravity may have been stronger or weaker during the universe's infancy, allowing matter to collapse faster and structure to form earlier. This could explain how those massive galaxies observed by Webb could arise so quickly, without rewriting every other aspect of the Big Bang theory. But it goes deeper still. Some scientists believe that space-time itself might have behaved differently in the early universe. In emergent gravity frameworks, gravity isn't a fundamental force, but a product of thermodynamic or quantum information processes. If that's the case, then early space-time might not have even followed the same rules of curvature and causality we observe today. In other words, the early universe may have had its own physics, now hidden beneath the veil of cosmic history. Could this be why we're seeing galaxies that shouldn't exist? Could their formation be governed by temporary laws, a different rule book during the universe's chaotic birth? If this is true, it would mean that the laws we observe today are only local approximations, a kind of cosmic consensus formed after the early chaos settled. And this raises a chillingly beautiful possibility that the universe is not a machine running on eternal rules, but a living system with evolving principles. A cosmos that breathes, shifts, and grows, not just in scale, but in law. Of course, these are bold ideas. Changing the laws of physics is not something science does lightly. It demands overwhelming evidence, extraordinary rigor, and a complete rethinking of centuries of theory. But the cracks are showing. From the nature of dark matter and dark energy to the unexpected abundance of early galaxies, the cosmos is revealing a tapestry far more complex than we imagined. At Infinity Beyond, we don't claim to have the answers, but we do believe in asking the right questions, especially the ones that make us uncomfortable, the ones that push us beyond what we thought was knowable. Because history shows that physics breaks right before it breaks through. In our next segment, we'll explore what lies ahead, the future of astronomy in a post-Webb world. How will upcoming telescopes, particle experiments, and AI-driven simulations reshape our search for cosmic truth? And could the next discovery be the final key to rewriting reality itself? Stay with us. The universe has much more to say. We stand on the edge of a cosmic revolution. The James Webb Space Telescope has cracked open a new chapter in humanity's understanding of the universe. But this is not the end of the story. It's only the beginning. As mind-bending as its discoveries have been, even greater revelations lie ahead. In this segment, we venture beyond the mystery to ask, what comes next? How will the future of astronomy evolve in a world where the universe itself refuses to follow the rules? First, let's talk about technology. JWST has already proven itself to be the most powerful space observatory ever launched. But it's not alone. A new generation of instruments is poised to expand our vision even further. The Nancy Grace Roman Space Telescope, launching later this decade, will have a field of view 100 times larger than Hubble's and will scan vast portions of the sky with unparalleled speed and precision. It's designed to study dark energy and exoplanets, but its wide-field infrared imaging could also uncover more of the ancient galaxies JWST has teased us with, helping determine whether they're anomalies or the norm. Then there's ESA's Euclid mission, already en route as we speak. Euclid will map the geometry of the dark universe, measuring the shapes and distances of billions of galaxies. It aims to understand how dark energy has shaped cosmic expansion, and may give us clues as to why galaxies formed so quickly in the early universe. Together, Webb, Roman, and Euclid will form a cosmic triangle, cross-verifying data, refining models, and confronting mysteries with sheer observational power. But technology isn't just orbiting above us. On Earth, the Vera C. Rubin Observatory is preparing to begin its 10-year legacy survey of space and time, LSST. It will take a full image of the southern sky every few nights, revealing transient phenomena, mapping asteroids, and building the largest time-lapse of the universe ever created. These aren't just instruments, they are portals, gateways to realities that remain hidden just beyond our current perception. And yet, it's not only what we see that matters, it's how we understand it. To that end, a revolution in data analysis and AI-driven modeling is transforming astrophysics. With billions of galaxies to catalog and model, machine learning is now at the forefront of cosmology. Algorithms trained on real observations and simulated universes are helping scientists find patterns no human eye could detect, offering new ways to test theories, challenge assumptions, and perhaps even predict discoveries before they're observed. Imagine an AI detecting anomalies in the formation of galaxies and proposing new physical laws to explain them. Imagine simulations that allow us to rewind cosmic evolution and run alternate versions of reality. We are no longer just observing the universe. We are beginning to simulate it, to interrogate it, to play with its parameters like knobs on a cosmic control panel. And beyond that, particle physics is catching up. Experiments at the Large Hadron Collider and the proposed Future Circular Collider are pushing deeper into the quantum realm, searching for hints of dark matter particles, extra dimensions, and physics beyond the standard model. If these experiments succeed, they could bridge the gap between the tiniest particles and the largest structures in the universe. Because make no mistake, the mystery of the early galaxies is not isolated. It is entangled with everything, with gravity, with quantum fields, with entropy, with time itself. In this unfolding age of discovery, the greatest tools may not be telescopes or supercolliders, but new ideas. Daring to question assumptions. Daring to ask, what if space-time itself is emergent? What if the laws of physics are the result, not the foundation, of a deeper informational process? These questions are no longer fringe. They are moving toward the core of theoretical physics. At Infinity Beyond, we believe the next great revolution in cosmology will not come from a single experiment or even a single theory, but from the intersection of all frontiers: space, time, matter, data, and imagination. United. In our final segment of this series, we'll pull all of this together. What the early galaxies tell us, what they demand of science, and what they mean for our place in the cosmos. Are we on the verge of rewriting the origin story of the universe? Or are we beginning to uncover an even grander narrative, one in which life, consciousness, and structure are not accidents, but inevitable expressions of a deeper cosmic order? Stay with us. The finale is near. The discoveries made by the James Webb Space Telescope have triggered a deep cosmic introspection, forcing us to look not just outward, but inward, at the very frameworks that define how we understand reality. So far, we've seen galaxies that formed too early, structures that seem too organized, physics that appears inconsistent, and time itself possibly acting in unfamiliar ways. But now we ask the boldest question of all. Is it time to rewrite the entire story of the universe? For over a century, cosmology has relied on a model born from the success of general relativity, quantum mechanics, and observational astronomy. The Lambda-CDM model, our standard model of cosmology, has helped explain everything from the cosmic microwave background to the distribution of galaxies on the largest scales. It's elegant, it's predictive, it's consistent, and yet, it may no longer be sufficient. Webb's observations of fully formed galaxies at redshifts above 10 and 12 challenge the very timeline that Lambda-CDM rests upon. If these galaxies existed when the universe was just a few 100 million years old, then either galaxies form much faster than we thought, or something is fundamentally wrong with our parameters. Let's examine the implications. First, galaxy formation theories may require a complete overhaul. Current models assume a bottom-up process. Small objects merge over time into larger ones, but what we're seeing suggests a top-heavy formation, where massive galaxies emerge quickly, possibly seeded by early black holes or driven by unknown forces. Second, inflation theory, the idea that the universe underwent a brief, exponential expansion right after the Big Bang, may be incomplete or inaccurate. If some regions of the early universe inflated differently, they could produce structures that appear far older than the global average. This introduces the possibility of cosmic variance on a far grander scale than previously assumed. Third, the very age of the universe might be in question. If redshift readings are being subtly skewed by gravitational or quantum effects, our entire cosmic distance ladder could be miscalibrated. In that case, the universe might not be 13.8 billion years old. It might be older. Fourth, dark matter and dark energy, two of the most mysterious components of our universe, might not behave uniformly across time and space. What if dark energy had bursts of activity early on? What if dark matter formed exotic clumps or filaments that accelerated galaxy evolution far beyond expectations? These questions aren't just tweaks to the model. They demand a new paradigm. Some scientists are already working on next-generation frameworks, ideas that integrate quantum gravity, information theory, and even consciousness into the fabric of cosmology. Theories like holographic cosmology, conformal cyclic cosmology, or entropic universe models are pushing the boundaries of what a scientific theory can encompass. These models suggest that the universe may not be a singular linear story, but a multi-layered narrative with echoes of past cycles, hidden dimensions, or informational flows that structure reality from the ground up. This is where cosmology begins to blur with philosophy. We are no longer simply measuring the heavens. We are confronting the nature of existence itself. Why is the universe structured? Why does it produce life, order, and meaning against the apparent entropy of everything? The early galaxies discovered by JWST might be more than just ancient lights in the darkness. They may be signposts, messages from the deep past, inviting us to let go of certainty, to evolve not just our equations, but our imagination. At Infinity Beyond, we believe that science isn't about defending dogma. It's about expanding perspective. Every contradiction is a clue. Every anomaly is a door. And beyond that door is not chaos, but deeper order, waiting to be revealed. In our final segment, we'll explore what this all means, not just for physicists or astronomers, but for you. Because understanding the universe isn't just about stars and galaxies. It's about our place in the story. And if the story is changing, what role are we meant to play in the cosmos? Don't miss it. The stars have spoken. From the farthest edge of the observable universe, across billions of years and endless stretches of time, ancient light has reached us. The galaxies we now see, formed when the universe was a mere infant, have shattered our expectations, redefined our theories, and challenged the very fabric of what we thought reality was. But beyond the data, beyond the science, there's a deeper question. What does it all mean for us? For centuries, we looked up at the night sky and saw chaos. Then we saw order, then stories, and finally, science gave us equations, measurements, and predictions. But no matter how advanced our instruments become, no matter how many galaxies we count, one truth remains. The universe is not just out there, it's in here. You are made of stardust, literally. The carbon in your body, the calcium in your bones, the iron in your blood, all forged in the heart of ancient stars that exploded long before Earth even existed. You are not a bystander in the cosmos. You are its latest expression. The discoveries made by the James Webb Space Telescope remind us that the universe isn't finished. It's still revealing itself, still unfolding, and we are part of that unfolding. Think about this. Those ancient galaxies, some over 13 billion light-years away, are not just distant in space. They are distant in time. When Webb sees them, it sees them as they were at the dawn of time, which means, in a way, we are witnessing the beginning. From the middle. And perhaps that's our role, not to observe the universe passively, but to awaken it to itself. You see, science tells us how the universe works, but it's up to us to ask why. Why does anything exist at all? Why does the universe make stars, galaxies, life, minds? Why does it make you? Some philosophers and scientists alike now entertain a provocative idea that consciousness is not an accident of evolution, but a fundamental feature of the universe. That intelligence, observation, and awareness might play a deeper role in the unfolding of reality than we've ever imagined. It sounds mystical, but it's grounded in the mystery itself. Every new telescope, every new theory, every ancient galaxy discovered invites us to re-examine not just what the universe is, but what it means to be alive in it. This is no longer just science. It's a story in which you are both the reader and the character. A story where the cosmos is not a cold machine, but a living narrative, one that is writing itself through time, gravity, light, and you. At Infinity Beyond, we believe this is the next frontier, not just deeper into space, but deeper into meaning. We believe that science should be beautiful, that wonder matters, that imagination is a tool of discovery, and that when the universe challenges what we know, it's also inviting us to become more than what we were. So as we close this journey through ancient galaxies, through shattered laws of physics, through evolving models and timeless mysteries, we leave you with this. The cosmos is not asking for your fear. It's asking for your curiosity. The unknown isn't something to run from. It's something to run toward. Because every photon of ancient light, every whisper from a distant galaxy, every theory rewritten, is really saying one thing: come find me, and we will, together, into the stars, into the questions, into the infinity, and beyond.